All right, so this video is going to talk about Lab 8, which is the conductimetric titration we did in class last week. And when you make your graph, you should find it looks a little bit like this. So it's going to look like a V, when you're looking at the conductivity of your mixture throughout the course of the reaction. And you can see underneath here, I have the net ionic equation written out, and this is on your lab handout as well. So some things to notice is we've got two regions of high conductivity, and then we've got this region of low conductivity. And we can actually identify this spot where we have the minimum conductivity, where in theory it should get close to zero. So we want to analyze why this is happening. So something that's important to think about when we're trying to interpret this graph is that what allows a solution to conduct electricity is if there are ions dissolved in the solution. So when you see high conductivity, that means there's a high concentration of aqueous ions. If there's low conductivity, that means there's a low concentration of aqueous ions. And we can look again at this balanced net ionic equation up here at the top of the page to figure out what these ions are and why the conductivity goes down and then up again. So what I have drawn here is your initial solution, which was just barium hydroxide aqueous. Whenever you have an aqueous ionic compound, it's always going to dissociate to form ions. So you can see why this solution initially is conducting electricity really well, because we have lots of dissolved ions in our solution, and those ions are barium and hydroxide ions. So if we go along and we start adding sulfuric acid is a strong acid, meaning it behaves kind of like an ionic compound and it dissociates into ions. And as you start to add sulfuric acid, for every one sulfuric acid you add, it will add 2 hydrogens and 1 sulfate. So what happens whenever you add a hydrogen ion, the hydrogen is going to bond with one of these hydroxide ions and turn into water. So notice how we just eliminated some ions right here and right here. So we no longer have ions present, we just have neutral water molecule. And then over here, any sulfate ions we add are going to react with the barium ions to form a solid barium sulfate. And these are going to collapse together and form a crystal lattice, which will be kind of hard to show in this picture. But notice at this point we've added just a little bit of sulfuric acid, and so a few of our barium and hydroxide ions have reacted, so our conductivity is going to drop a little bit, but we still have lots of barium and hydroxide ions present. So right now we're at the point where there's excess barium hydroxide present in our solution. So we're still conducting electricity really well. That's because there's still lots of barium hydroxide ions around. If we add a little bit more sulfuric acid, remember every time I add some sulfuric acid, a hydrogen is going to react with a hydroxide to form water. And so there goes those ions. And then the sulfate is going to react with the barium to form a solid. So there goes those ions. So see our conductivity will drop a little bit more. You add a little bit more sulfuric acid. Again, we eliminate these ions because we've turned them into water. And then when we add another sulfate, that's going to eliminate those ions because it's going to turn into a solid. So remember, ionic solids do not conduct electricity well. In order for it to conduct, the ions have to be dissociated in aqueous form and moving around freely. So this solid barium sulfate right here is not conductive. It's only aqueous ionic compounds that conduct. So when we add let's add one more kind of dose of sulfuric acid, and then so if we stop at this point, notice we have added equal amounts of both of our reactants. And we call this the equivalence point. And what's significant in this reaction is when we've added equal amounts of both of our reactants, all of our ions are used up. And so everything is in either the solid form, so all we have left at this point is the solid form of barium sulfate or liquid water. So we have entirely products. And remember, these two things are not conductive. So that means at this point, when we're at the equivalence, when all of our ions are used up, our conductivity should be pretty close to 0 because all we have is these two substances, a solid ionic compound and molecular water. Those do not conduct electricity very well. So that's going to be, so when we look at our graph, that dip in the graph is our equivalence point, and that's how we know at that point we've added equal amount of sulfuric acid as we had barium hydroxide to begin with. And then if we keep going beyond the equivalence point, what we'll see happening, and we'll use a different color here, what we'll see happening is we keep adding more sulfuric acid. So now, when we go beyond the equivalence point and we add sulfuric acid, there's nothing in the solution left for it to react with. So there's no bariums and hydroxides around. So as we add more sulfuric acid, we're just adding more and more ions. So the solution is going to start conducting electricity again because I'm adding excess hydrogen and sulfate ions. So initially we got a high concentration of barium and hydroxide ions. At equivalence, all of your ions are used up. So we reacted all of our barium hydroxide ions. Everything is in either the solid or liquid form. Past the equivalence point, we start adding excess sulfuric acid, and so our solution starts conducting electricity again because we're adding excess ions from the sulfuric acid that's being added. So if we look at it on this graph, this region right here is the region where we have excess barium hydroxide. So we have lots of aqueous ions there. Over here at this dip in the graph, this is our equivalence point. And this is the point at which the moles of barium hydroxide that we had to begin with is equal to the amount of sulfuric acid which we added. And then over here, the second region is where we have excess sulfuric acid. So again, these regions conduct electricity well. Over here, it's because there's hydrogen and sulfate ions floating around. In this area, it's because we have free barium and hydroxide ions. So thinking about what we can do with calculations here. So we can do a titration calculation with this as well as a gravimetric analysis titration. So walking through these steps, what is the volume of H2SO4 at the equivalence point? So what you want to do here is you want to look at your graph. And this volume right here at the dip, that is going to be your volume at equivalence. So for most of you, I think your volume at equivalence was probably somewhere between 8 to maybe like 22 mils, depending on which sample you were given on which day. So it should be somewhere in that zone. I know it's a pretty wide range. Each group can have a different answer. So don't compare your answers with other groups. We use different samples, so they're all going to vary a little bit. How many moles of sulfuric acid were added at equivalence? You know the molarity of the sulfuric acid was 0.100 molar. And with a solution, if you know molarity and you know volume, you can find moles. So you can use your volume from this graph right here, the molarity that was given to you, and molarity times volume will give you your moles of acid. If we know moles of sulfuric acid at equivalence, remember I said the equivalence point, moles of H2SO4 is going to equal moles of barium hydroxide. Because if you look at the chemical equation, we'll see it's a 1-to-1 mole ratio. Okay. What volume of unknown solution did you use? It should be somewhere around 10 mils. Hopefully you recorded an exact volume. I don't know if it was 10.0 or 10.5 or 9.5. Whatever you got for your volume there. And then molarity of your unknown solution, your molarity is your moles over your liters. So you found moles right here, your volume is right here, so you should be able to find the molarity of your unknown solution. Okay, gravimetric analysis. This is another way of finding the molarity. In theory, this should give you an answer pretty similar to problem number 5, but we might see some variance here. So use your mass data to determine the grams of barium sulfate collected. So you have to look at your mass data. You want to look at your final heating, which would be your dry, solid, and the filter paper. And you want to subtract from that the initial mass of your filter paper, right, to get the mass of your dry solid. Your dry solid should be pure barium sulfate. Moles barium sulfate. When you know the chemical formula of something, and you know mass, you can look on the periodic table. So you can look on the periodic table and calculate the molar mass of barium sulfate and convert that mass into moles. Moles of barium hydroxide. So here you want to look at your mole ratio from the balanced chemical equation, and this one's straightforward. It's a 1-to-1 mole ratio. So I should put the one over here. So if you look over here, for every 1 barium sulfate that you make, you used up 1 barium hydroxide. So there's a couple different ways of doing it, but the way I typically think of it for a stoichiometry problem is I think, well, I know moles of barium sulfate, that's the thing I collected. I look up at this balanced chemical equation, I can see there's, for every 1 barium sulfate I made, I used up 1 barium hydroxide. So 1 barium sulfate, 1 barium hydroxide. It's a 1-to-1 mole ratio, or you can think of it as, you know, the moles of barium hydroxide and barium sulfate must be equal. However you think of it, however you show your work there is fine, but the big thing is a 1-to-1 mole ratio. So moles barium sulfate will equal moles barium hydroxide. And then now you've got moles barium hydroxide. You know the volume, remember the volume of your sample should be somewhere around 10 mils probably. Hopefully you wrote down exactly how much you used. And molarity is moles over liters. So you find your molarity of your barium hydroxide solution. And then the last problem, unfortunately, we don't really have a good true concentration of your solution. So I'm actually going to revise this problem a little bit. And I want you just to say, which method do you think is more accurate? So which value do you have more confidence in? Your titration value or your gravimetric analysis? So it's helpful to think about which kind of method do you think gives you better data. And then I want you to explain at least one reason why. So you could either think of it as, let's say you think titration is more accurate, give a reason why you think titration is more accurate, thinking about the actual experimental process, or you could say, give a reason why you think gravimetric is less accurate, or vice versa. If you think gravimetric is more accurate, give a reason why experimentally. So that's what we want to do for problem number 6. So it's kind of open there, as long as you have some logical justification for why you think one way is better than the other. I'll accept either answer if you've got valid reasoning. All right, so email me if you have any questions or come by tutorial.